following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
So I hope in time for you to consider this material also for in thinking about projects, because there are lots of experiments to do with these. I did a little MATLAB experiment that I'll mention, and I guess it was too small because it didn't make multigrid look as good as it is. So can I remember the steps of multigrid, and then you will remember why we take those steps, and then make a sort of basic analysis of how do you decide whether this multiple step process is successful? How much does it reduce the error? So you remember the steps. Oh, thanks. So the first step is really a little bit outside multigrid. It uses an ordinary iteration like Jacobi a few times. And so you remember that the matrix that governs this ordinary step, the matrix that's crucial for this is the what multiplies the error at every step. So we have initial error, and if we take a smoothing step with a preconditioner P, then the error is multiplied by I minus P inverse A. So that's the matrix. That's sort of the one step, one iteration matrix for ordinary iteration, where A is our, of course, we're solving AU equal B. That's our problem. The matrix P is close to A. Of course, if we took P equal to A, then the error would be reduced to 0 right away, because we would be solving the system one shot. But now we're left with some error, and this steps 2, 3, 4 reduce it further. And our hope is to see that this multigrid operation reduces the low frequency part, because this one will act successfully on the high frequency part, the oscillating error, but smooth error, for smooth error, the eigenvalues here are too close to 1, and it's too slow. Okay, so I was just going to track down, well, first have to remember what are the pieces here. So there's a matrix R, restriction matrix, a matrix A2H, which is the original matrix A, or AH, I could call that. The original one is on the fine mesh. So I need a coarse mesh version. And then, so that's what I solve on the coarse mesh, the smaller problem, and then interpolate back with a matrix I back to the fine mesh. Okay, so can I just remember also what those matrices, we have all the pieces really. So if I remember what R and I are, okay, so let me write down all those pieces. So A is, let me tell you the MATLAB experiment I ran. So A is our 2's and minus 1's matrix, our second difference matrix, in 1D, to keep it simple. And it should be divided by h squared. And so that is on, well, I guess we took the mesh with where the coarse mesh just had 2 interior points. The value at the boundaries was 0, and the fine mesh has 5 interior. So this will be 5 by 5. Okay. Then we needed the restriction and interpolation matrices. So this was R, the restriction. So the restriction, which we're going to use right away, will take us from the find to the course. So that matrix will be, it'll multiply things with 5 components and produce an output with only 2 components corresponding to those mesh points. And the numbers were 1, 2, 1, 0, 0, and 0, 0, 1, 2, 1, and needed to divide by a fourth because those rows added up to 4. The idea being that if we restricted all ones, we should get all ones, and we need that 1/4 factor to do it. And the interpolation went the other way, and it was essentially the transpose. That's the nice connection between, nice connection to have, and again, we need a factor. Oh, and maybe the factor is a half there. Good. So those, we've now got all the pieces except A2H, and I think just at the very last minute last time, I said what A2H should be. And the good choice for A2H is to, because so that's on the coarse mesh, right? So that's going to be small matrix. So the good choice is I, which puts it up on the fine mesh, AH, which is our operator on the fine mesh, and then R that restricts back. So RAI is the right construction for it's sort of the natural construction for the coarse mesh operator. And notice, I don't know if you appreciate having this. This is the same as R transpose with some factor, so that it'll come out symmetric. It'll come out positive definite, and actually it'll come out, in this example, it will come out exactly the second difference operator on the coarse mesh. So this will turn out to be 2 minus 1 minus 1, 2, the 2 by 2 operator, and since we're on the coarse mesh, the step size is 2H. I won't do that multiplication, but MATLAB confirmed it. Okay. Now, so that's where we were. So I've sort of done now a recap of multigrid. And I'm ready to tackle a little understanding now of what happens to the error. So at this stage, I end up with some error. UH is not the exact answer. I have an error EH, which is U minus UH. That's the error. At the end. Okay. Now, question is, what happens to that error? Can we see how and why it's reduced as we do a V cycle, as we do a 2, 3, 4 cycle? So, since everything's linear, that error is multiplied by some matrix, and we just have to track those steps, see what that matrix is, and look at its eigenvalues. So that's my goal here, is to find the matrix, call it S, that takes a step, a multigrid step, and what does it do to the error? Okay, so can I just follow that step? All right. So here's the key matrix. Maybe I'll write it underneath here. Okay. So what happens to the error? First of all, I have, let me write the steps down. EH then is U minus UH. That's entering multigrid, that's my error. Okay. Now I compute this residual, RH. which is, I want to say that it's A EH. Can I check that that's true? Yes. A times this is A times U, that's the B, minus AH times UH, that's the second term. So that's okay. So that's what happened there. Then it got restricted. So now I'll keep a record of what happens to EH. So it's multiplied by A to get the residual. Because we work with the residual and with B because B is the input we know. Then at this step 2, that residual is restricted by R. Now we've got R2H, right? When I multiply by R, I've got R2H. Okay, next step, to get to E2H. So what do I do there? I multiply by the inverse. I solve this system, so of course I don't actually find an inverse matrix, but that's the formula to get this. I multiply the inverse matrix by that, so I've got an inverse matrix here. Shall I write it as A2H inverse? This was AH. Okay. Now when I multiply by A2H inverse, I'm this far. And the final step multiplies that by I. So there you go. It looks pretty awkward. But that's the matrix S that produces EH. So I'm thinking that my matrix is going to be called S. This matrix here is going to be called S. So let me write down what S is. It's just, all I want to do is remind us what A2H is. By this choice there, it's RAI. And then comes R, and then comes A. A is now AH. Well, we've got a matrix. And for this example, I can compute what it is. Can we say anything about that matrix from its formula? It looks a little messy. But, of course, it's built out of these pieces. It's built out of the given matrix A and our R and our I. And there is a neat property hiding there, which you can see if you square that matrix. So look at S squared. If we look at S squared, so this is the matrix to understand now. And I don't claim to understand it as well as I would like. But, so this is the matrix for these 3 steps. We would have a full multigrid V cycle, just before I lose the track on that. A full multigrid V cycle would do M a few times, say twice, 2 smoothers, then it would do a V cycle, and then smooth again. Well, I should have said the smooth again would be the one on the left. This is the original. So this 2 smoothers, followed by a multigrid cycle, followed by a couple of smoothers. That would be our total overall matrix. But I want to focus for right now on this matrix S, and I guess I hope that anybody who does a project or a homework on this topic, you're going to create I, R, and A and compute S. And it should show what S squared is. So could I look at S squared? You'll see why. So I just write S down twice. RAI inverse RA. So that's once. Now I'll repeat the whole thing. I, RAI inverse RA. So that's, I've multiplied S by itself. And what do you see? Well, it's nice, right? If you look at this, you see that we've got this combination RAI sitting in the middle, because when I did it twice, the RA came from there, and then an I was at the start. So this is, so what's left? S. This matrix S is equal to its own square. S squared equals S. You know, we've got this, we're able to see this without, this would apply for this example, but for all examples. Now, now I'm ready to think about eigenvalues a little bit. What does that tell me about the eigenvalues of S? I mean, so this is a small class of matrices with this property that S squared equals S. And maybe I say something about those here. So if S squared equals S, what does that tell us about eigenvalues of that matrix? It's a square matrix. It doesn't happen to be symmetric. Very often we're looking at symmetric matrices, but this is a little lopsided. We have an A off on the right. I might be able to make it symmetric by bringing part of that A off to the left, but this is the main point. What are the possible eigenvalues of that matrix S? Well, 0 and 1. The only eigenvalues are 0 and 1. Why is that? Because if SE equals lambda E, so I'll put that word if in. If SE equals lambda E, I could multiply by S again, so I would get S squared E equals lambda SE and that's lambda squared E, right? I haven't done anything fancy here. All I'm saying is that any matrix, if it has an eigenvalue lambda and an eigenvector E, then S squared has that same eigenvector, and its eigenvalue is lambda squared. But now, S squared is S. So this is the same as SE, which is lambda E. You see that I now have lambda equal lambda squared. Sorry, I probably made that take more time than it had to. If S squared equals S, then lambda squared equals lambda. So I have lambda squared equals lambda, and the only two possibilities, that's a quadratic equation, it's got two roots, and those are the roots. If lambda squared equals lambda, then lambda could be 0, or it could be 1. So what does that tell me? That tells me that the eigenvectors that have eigenvalue 0, what happens to those in multigrid? They're killed. An eigenvector with an eigenvalue of 0 means that SE is 0. So whatever error we started with, one cycle through multigrid will remove it. Okay, so these are these are in the null space of S. They're vectors that S completely removes. And these are vectors where SE equals E, the eigenvalue is 1, and multigrid does nothing. So, well, one part of the message then is that I could use multigrid. Well, I guess I hadn't thought about this, but one message is don't repeat 2, 3, 4, right? That would be a large waste of time. If you just repeated, if you just did another V cycle and didn't do any smoothing or anything in between, then the error that came out of the first V cycle would survive right through, Nothing good would happen in the second cycle that didn't already happen in the first. Now, and another message is, of course, I could do multigrid forever and I'm not going to get convergence. Actually, that's sort of interesting because we're totally accustomed to working with matrices M such that whose eigenvalues are spread out but below 1. This has its eigenvalues not spread out at all, 0 or 1. That's it. Okay. And I had better say quickly that the key matrix here is I minus S, just the way it was I minus P inverse A. So the multigrid matrix, yeah, maybe I could have messed up. The multigrid error matrix, the matrix is really I minus S. So let me be sure I see where that happens. I guess I got down here to figure out what EH is, and then I didn't do anything with it. I forgot to write in the key step that at the end of step 4, when I have the piece of the error, then I add that to UH. So add UH plus this estimated error. See, if I knew EH, if I knew small EH, the exact error, then when I added, I would get U, the answer. Of course, I don't know that. What I know is capital E, so that's a cap E, which will agree with E on some of these, but not others. So, all right. I guess I'm seeing the problem. I may have had it in reverse because it's I minus S that's crucial. So these are errors. What happens to them? Are these the good ones? I think they're the good ones. Is that right? They're the good ones because the errors in this stage, S gets them, multigrid gets them exactly, so that when I add this in, it's right on target. It's accounted for. So these are ones that multigrid fixes. Because of course everybody recognizes that I minus, let me just say it though, that I minus S times those errors is 0. So the eigenvectors with eigenvalue 1 are the ones that are perfectly captured by EH has got those components of small EH exactly right when I add them on perfection. But then there are other components which it hasn't got at all. And when I add those on, no change, no improvement. Okay. By the way, how many eigenvalues, so these eigenvalues are repeated. Like here, I've got 5 by 5 matrix. How many zeros and how many ones are going to be? You could say it's a projection matrix. It projects, S projects onto these eigenvectors. I minus S projects onto these eigenvectors. And how many zeros and how many ones for this if A is 5 by 5? Well, what is A? This A is 2 by 2. So if I look at my S, look at my nifty formula for S, do you see all this here? Let's just get the sizes. A is 5 by 5. R is 2 by 5. It shrinks us down to the coarse mesh, which is only where this is only 2 by 2, and this takes us back up. So the total result, 5 by 2, 2 by 2, 2 by 5, 5 by 5 is 5 by 5. But what's the rank of S? Small prize for telling me the rank. how, I'm interested in this count. How many vectors are killed? How many go through unchanged when I multiply by S? So what's your guess for the rank of S? 2, exactly. So S will have 2 of these guys. 2. This has multiplicity 2 in the 5 by 5 case, and this one has multiplicity 3. And these are, so multigrid is only fixing 2, getting 2 vectors exactly right, and not getting these right. Well, I mean, 2 is half of 5, right? Well, in fact, 2 is exactly half of 5, because, well, if I went up, it would be 3 and 7, 4 and 9. The point is that the number of coarse grid points is about half the number of fine grid points. So 2 is about half of 1, 2, 3, 4, 5. Yeah. Of course, how could I expect better than getting 2 perfect? I can't expect more because the problem I ultimately solve here is on the 2 by 2 size. So when I actually do something useful, I'm only doing it on the coarse grid, and that's got dimension 2, and so there will be 2 eigenvectors that get perfectly fixed, but the others don't. Okay. Now, I do have to think which are the eigenvectors? What eigenvectors are there? And so I guess what I hope is, what I believe is, that these eigenvectors, which multigrid gets exact fixes for me, those E's, well, the E's have 5 components, right? We're in, our matrix S is 5 by 5. But I guess I'm expecting that the eigenvectors, that these 2 are somehow basically on the coarse mesh. And that these 3 that don't get fixed are somehow basically orthogonal to the coarse mesh, I would say. That these will be low frequency vectors and these will be high frequency vectors. That's what I expect. And that's what somebody who's, I mean, there are whole books on multigrid where the main step in the analysis is to see that those eigenvectors are, as I described, sort of coarse mesh vectors that are fixed and fine mesh vectors that don't get fixed by multigrid. And those are the ones that the smoother better deal with. Okay. Can I mentioned that just before class I did a MATLAB experiment, and I actually did it on these matrices with the Jacobi smoother. And I wrote down the numbers here somewhere. And actually, I was a little disappointed. 5, but I came away saying, okay, 5 by 5 just wasn't big enough. So I'll put down what I've got. Okay. So, well, what did I get for the eigenvectors, eigenvalues of S? I got 1 and 0. That was a good thing. Okay. Now, did I write them down? I sure hope I did. Yep. Okay. So the question is, what about when M is in there? So the exercises were find the eigenvalues. Well, it'd be interesting, first of all, to know the eigenvalues of M. This is the Jacobi smoother, weighted Jacobi. Then here's the one here's one we're really interested in. We're interested in doing a smoother, doing a multigrid cycle, and doing a smoother. And I guess I'm hoping that those eigenvalues are below this. So this is one smoother, and this is smoothers with multigrid, and this would be 2 smoothers and 2 post-smoothers. So repeating Jacobi twice, and m cubed would be interesting. So here's what I got for these things. Okay. So what do I know about the eigenvalues of m? Do you remember that we actually worked those out? For ordinary Jacobi, they're cosines, and for weighted Jacobi, that weight omega, which I chose to be 2/3, comes into it. Anyway, so in the 5x5 case, well, it's the biggest one that we all really want to know. And the biggest one, so this is the maximum eigenvalue. Let me just write down the maximum. So the maximum eigenvalue of m was 0.91. So that says that ordinary Jacobi on a 5x5 problem reduces the error by that factor at every step. And of course, that factor is totally satisfactory. If we could always do that, we wouldn't need to do multigrid. But that 0.91, if I go to 7x7 or 9x9, it's going to quickly move up toward 1. So that's an indication that my little experiment here is a bit small, because that's not as near 1 as a true thing would. Okay, then what was the result after this? I'm sorry to say that it was 0.88. Disappointing. So I did this one. I did 2 smoothers. Well, of course, that's going to give me 0.91 squared in there, but anyway, I got 0.64. Okay. So which of course is very good if we could, well, I'll say very good, but actually for that size I had hoped for better, because my impression of multigrid from reading about it is that, a good multigrid cycle, but this is probably it has a eigenvalue of about 0.1 is the goal. So how is that achieved? Well, I don't want to achieve it by just doing a whole lot more smoothing. Actually, it's achieved by doing a whole lot more multigrid. Instead of doing just a little V cycle, this would be the thing for a good, deep V cycle that went down maybe 4, and maybe a W cycle, do it twice. Then, of course, this is for a big problem, but really making multigrid work, like a W cycle. Or even there's something called full multigrid. Shall I draw the picture that corresponds to W for full multigrid? So full multigrid, you start on a coarse mesh, go up, back, back, maybe twice, up to this level, back, and up again. So that's called full multigrid. Gives the best numbers. Anyway, we get numbers like this for when we really do more, and it's very much worth it. I mean, it's completely a success. Okay, I would be interested to see a little. Well, I guess what I'm going to do now is, for this model problem that we worked on, I could find these eigenvectors, E. And and understand the whole, and analyze this model problem. Okay, so how to find these eigenvectors? Again, for these particular matrices. Well, let me start with the eigenvalues of eigenvectors of A itself. Do we know the eigenvectors of A? This is, I guess if I had one important matrix whose eigenvector, one and non-trivial, I can't look at the 5 by 5 there and guess, at sight, say what the eigenvectors are. So everybody sees it's 5 by 5 with 4 minus 1s below, 5 2s on the diagonal, 4 minus 1s above the diagonal, and the eigenvectors of those special matrices have a special form, so which allows us to do everything here. I could. So what can I do here? I can do the computation of what S is. Maybe I should. Can I report on that, which will be in the notes? Let me tell you what S is. If I take that as R, that as I, that as A to H, I get S to be this matrix. Column of zeros, 1/2, 1, 1/2. Column of zeros, 1/2, 1, 1/2, and column of zeros. So it's rather remarkable in this particular case. Now, what can we recognize from this? Well, can we see the eigenvalues of S from explicitly from the matrix? Well, we certainly see that it has rank 2, right? It has 2 independent columns, so its rank is 2 as we predicted. So it will have 3 0 eigenvalues. And we can see what the eigenvectors are, actually. What are the eigenvectors? If I go up above here, can I do that? I want to go up and say something about the eigenvectors here with eigenvalue 0. What's the null space of that matrix? If I multiply S by vectors, I want to get 0 vectors. Okay, the eigenvectors E for lambda equals 0. If I multiply by anything with a first component, nothing in the with these 3 components, do you see that if I multiply, SE is 0 then for these E's. In a way, that's exactly what I hoped for, that these vectors E are the vectors that live on the fine grid but with no component on the coarse grid. And they're the ones that which have SE equals 0, and multigrid doesn't help. Multigrid doesn't help. I minus S times those vectors is those vectors. No improvement. So they're eigenvectors with eigenvalue 0 for S, but with 1 for I minus S. Okay. So those are the ones that, and are those, see, my general thought is those would be the high frequency eigenvectors, the high frequency vectors. They're sort of high frequency. But they're not low frequency anyway, because low frequency, these would be a smooth vector E. Okay, so what are the eigenvectors with the other 2 eigenvectors, the ones that multigrid fixes? Okay, so I'm looking for the other 2 eigenvectors here. And how do I find them? Let's see. Let me see if I can even do it for this matrix. So So I'm looking for the eigenvectors with eigenvalue 1 now. So I should subtract the identity from this matrix. So I'm going to, when I subtract the identity, the 1s become 0s and the 0s become minus 1s, right? That's S minus I now. Try to keep a running equation that's correct. That's S minus I. And I'm looking for the null space of that now. Okay. Am I going to find it? I don't know. Do you see immediately what? That has a two-dimensional null space. There are two vectors. And can you see what they are? Well, what do you think? Yeah. We certainly could. I don't know whether... Anybody see a vector that's in the null space of that matrix? Let me just start and try to get one. So I'm looking at that matrix, looking for a vector in its null space, and that will be an error vector that Multigrid totally fixes. So if I start with a 1 up in that first component, then the first row will force me to have a 2 there. Is that right? And then the next row, and then I fixed the first row. The second row is all zeros already. Then I have 0.5 of that, which is 1. Oh, well, let me start from the bottom here. Well, it's probably symmetric. What do you think? Maybe something like 1, 2, and what's that middle number? Maybe 2. I guess I think that is in the null space of S minus I. Because if I multiply by the first row, I get minus 1 plus 1. And the second row gives me, the third row gives me 1 minus 2 plus 1. And the last, yes. So that's one of them anyway. And the point about it is it's pretty smooth. So that's what I anticipate, that vectors with that vectors that are smooth that's the type of vectors we're going to find multigrid fixing. So I've got one more eigenvector to find. Maybe I'll leave that as a puzzle for somewhere there's another eigenvector. Guess I'm not sure where it is. But I think it should be smooth. Yeah. Okay. Somewhere there is one. Okay. So can I now go away from this numerical example to give you the answer for this problem, but for any size? So the notes, it's because we know the eigenvectors of A. I started to talk about the eigenvectors of A, and I didn't finish. Okay, so let me, if I want to get formulas for these, I need to know the eigenvectors of A. So A, this matrix of 2s and minus 1s, the eigenvectors of that matrix are discrete sine functions. So an eigenvector would be, for example, sine of pi on 6, sine of 2 pi on 6, up to sine of 5 pi on 6. It's worth knowing that that those are eigenvectors. And other eigenvectors would be double the frequency, triple the frequency, 4 times the frequency, and 5 times. So the eigenvectors of this matrix are the discrete, what I will call discrete sines. Discrete sine vectors. And why? Because this matrix it builds in the boundary condition, since this there should be a minus 1 there, but it's chopped off. That minus 1, if it was there, would multiply the 0th component. But the 0th component is removed, so we have to be sure that the 0th component would have been 0 anyway, and that's the point. You see, if I follow this pattern, the 0 component that I'm missing would be sine of 0. The component I'm missing up here would be sine of 0 pi over 6, which is 0. And the component that's missing down at this boundary would be sine 6 pi over 6, which is sine pi, which is 0. So this is like that choice of vectors is the perfect Fourier vector. I expect Fourier when I see constant coefficients there, with the right boundary conditions 0 at both ends. Okay. Anyway, those are the eigenvectors. The kth eigenvector would have sine k pi, sine k2 pi, down to sine k5 pi, all over 6. And I'll just, in the remaining moment, write down the result of following through those vectors and finding finally the eigenvectors of S itself. Okay, so this is like multigrid in a nutshell, if I can find it. Multigrid in a nutshell. All right, better be on this final board. Okay, I minus S times this sign vector, the kth sign vector that I wrote over there, and I minus S times the n minus kth sign vector. So these will be low frequencies for small k, and these will be high frequencies. And it turns out that these are a half 1 minus the cosine of k pi over 6, or n plus 1, times yk plus, or sk, sorry, sk plus n minus k. And this, acting on the high frequencies, is a half of 1 plus cosine k pi over 6. sk plus n minus k. What am I seeing there? If let's just accept the algebra that went into this and see, does that tell me what the eigenvectors of I minus S are? Because that's my goal. Well, it does. Look, if I add these two equations, let me look first just at this equation. So this says that if I start with a low frequency, k small, low value of k, that it's nearly removed, right? If k is very small, the cosine of k pi over 6 is somewhere near 1. Of course, 6 was a little feeble. So let me take n, bigger matrices. Okay. Then the low frequencies are the ones where this cosine is near 1, this number is near 0, and they're practically removed. Where the high frequencies, not much happens, because the cosine is near 1, this number is near 2, I divide by 2, and it's near 1. So the overall picture is right. Now, to pin it down, if I add the two equations, then I get this combination sk plus s minus k. Oh, in fact, I guess I see it. What happens if I add the two equations? I get I minus s times sk plus s n minus k. And what do I have on the right-hand side? Well, 1. These add to 1. So I get sk plus sn minus k. Those are the eigenvectors of I minus s with eigenvalue 1. Yep. So they're the ones I found here. They're the eigenvalues of S with eigenvalue 0. These are the SKs plus S n minus Ks. And they live completely on the mesh points that are in the fine but not the coarse mesh. And then if I play around one more step, I can find the eigenvectors for the other eigenvalue, the ones that are basically low frequency and that where we have a numerical example. Okay, I've run out of time before I can do that last bit of algebra. That will be in the notes, which we'll get onto the website Monday at the latest. So I hope you have a sort of picture of what MATLAB, of what Multigrid does, and the experiments that you might do to check it out. Okay, I'll see you Monday, and we'll take a little more time to discuss projects because we'll have material on the web to work with. Okay, thanks.